welcome from my side. My name is Reiner Zitzmann from CAN Automation. I'm the General Manager of the CAN Automation GmbH, so the commercial arm of the CAN Automation Association. So I'm running the office here in Nuremberg, and we are the service provider of the association. So when the CAN Automation Association wants to offer services to its members or to place them on the market, then my team and myself, we are trying to assist the CAN users in the best and intended way. Yeah, who is CAN Automation? So why we are doing such things as today, such CiA webinars. So CAN Automation is an association that has the objective to increase the awareness of CAN, of controller area network-based solution and technology. So we are the international users and manufacturers group that develops and supports CANopen and other CAN-based higher layer protocols. So the non-profit group was founded in 1992 to provide CAN-based technical product and marketing information. The association fosters the image of the CAN technology and also provides a path to future network technologies. So we are doing this since 1992. And since these days, we have established a huge social network, so to say. So we know many players in the CAN technology, and you can benefit from this social network. So in case you are working in CAN-based projects, you are facing some CAN-based challenges, then there's always a good idea to contact CAN Automation, and we can maybe directly assist you, we can directly help you further, or at least we can rely on our huge social network. And typically we know there are people that can assist you, and we can direct you to them, we can establish direct contacts so that you can accelerate with your project and overcome the challenges. So briefly to our history, as I've already said, founded in 1992 with the objective to keep the awareness of CAN high. Therefore, we have CAN newsletter, a magazine that appears quarterly and that illustrates where is CAN used, to which markets the CAN technology has now already propagated, and which markets have been entered by CAN, where is CAN successfully used, or which new developments in the CAN technology itself do exist. So you see, on the one hand, we have our publications. On the other hand, we go to fairs and discuss with people why it is reasonable to use a CAN-based solution in this or that application field. And finally, we are generating CiA specifications. So if you have had a look already to the CAN standard, then you will know, well, in such a CAN standard, maybe a physical layer option or the data link layer has been standardized very good, very precisely. But to achieve interoperable products, there's a little bit more to know. So for example, how should be the data content of a CAN telegram organized, which kind of physical layer option you like to apply, in which way in your device. So all these things you need, for all these things you need an agreement. So from your side and the project partners, so that you have at the end of the day interoperable products. And we at CAN Automation, we pave the ground, so a neutral ground, so to say, that you can meet with your project partners and you can discuss how can we achieve plug-and-play capable products at the end of the day, developed independently from each other. And if you meet as a device, as developer, system integrator with products from all these manufacturers, then they show a high degree of plug-and-play capability in a given system. So you save a lot of configuration effort and stress. So this is one of the benefits of standardization, and we are supporting this. What you see also on this slide, that over the last years, the last decade, a lot of new development came up. So there was the CAN with flexible data rate presented at an international CAN conference organized by CAN Automation. It was the 13th CAN conference in 2012. So now this CAN with flexible data rate is already in cars. This CAN with flexible data rate is, so to say, in use. And there had been also a group at CAN Automation that said, well, it would be nice if we can benefit from the advantages provided of CANFD from the position of a CANopen protocol stack. Therefore, there was the need to update the CANopen protocol. The result was then the CANopen FD. And when we were ready with that, then there was the started the CANXL project. So CAN was extended data lengths. So this is, so to say, the third generation of CAN. And in 2021, there was the first presentation of this. We finalized the CiA specification of CANXL data link layer. So this is now currently under standardization. And you see a lot of development is ongoing in the application field of CAN. And therefore, it makes also sense to have a look what's going on in CAN with special regard to CANopen. CAN is still a hot topic. We see here the development of the CiA members. So there's still a growing number of companies saying, well, we think it is reasonable to get first-hand information on CAN-based technology, on the CAN developments, and therefore we sign our membership. It's a based fee-based membership, and we see here we have now at the moment 758 members. So it's still a growing number of companies that become CAN automation member. What is also an indication that CAN is still a vivid technology, and CAN has this relevance in automation technology. So what is CAN in automation doing? So we are developing and maintaining CAN automation specifications. So as I've already explained at the beginning, we try to assist people in achieving CAN-based devices that show in a given system a certain degree of plug-and-play capability. We accompany the international standardization of CAN technology, so the update of the ISO 11898-1 and 2 with regards to CANXL, for example. We integrate CAN-based technology in vertical markets. They are in relevant ISO and IEC standards. So this is the main part of our work. In addition to that, we allow some or do some marketing for these specifications and standards. So therefore, we have our CiA publications, such as the CAN newsletter, the printed version, online version. We have a kind of product overview in form of our product guides available on the CAN Automation website. And we have several brochures typically generated for certain fairs where we try to convince people why it is reasonable to offer CAN-based solution in this or that market. On the other hand, we provide technical education. So we offer open seminars, in-house seminars, testing services. So we offer services for marketing-oriented people, technical-oriented people, so system designers, device manufacturers, decision makers, and so on. Yeah, this brief overview about CAN in automation, so that you know how is CAN automation organized. CAN automation is organized in a very democratic way. So we have the CiA General Assembly taking place once a year, and then from that we elect our board of directors, the business director, the managing director, the technical director. At the moment, the business director is Christian Schlegel from Christian Schlegel Consulting, the former ICSA general manager. And he and his team, he are determining where is CAN automation doing some marketing, and where is CAN automation spending some money for assisting people in using CAN, for raising the awareness of CAN, and so on. And on the other hand, we have the technical director. Currently, this is Mr. Magnus Hell from Finland, and he and the technical committee, they are deciding how is CAN automation writing specifications, in which application fields we are active with our standardization activities, negotiating in case there are some upcoming competitions between some CAN automation working groups, and they have to negotiate between these groups and to find a solution that we have just a single specification for a certain issue. So this is then the technical committee, And the third one is Mr. Holger Seltbanger. So he's the managing director and he's my communication partner, so that I know exactly what is demanded by the association, and on the other way around, that I get the feedback that is provided the services in the way intended by the association. So you get a brief idea. So what's I think important for you is, if you want to contribute in CANopen automation, if you want to benefit from CANopen automation, then you should know, okay, there exist some CiA groups. So for example, the marketing groups, we have there at the moment a very active CanXL marketing group, generating brochures, website, fair presentations, where we say why it is reasonable to opt for CanXL, what is upcoming at the horizon when I think about CanXL. So this is everything done by the CanXL group, also initiating of Plugfests. And on the other hand, we have there a lot of technical working groups. We will touch these items addressed by these working groups also today. So we have there the technical committee that is dealing, for example, with the issue bootloader. How can I have, for the various CANopen generations, harmonized strategy of updating device firmware via the CAN interface? What means CAN communication, CANopen communication? Also here, the task force modeling is discussing how to describe CAN communication in the best way, that I have a specific meaning for certain terms, not to avoid that several working groups use the same term for different meanings. So it sounds very simple, but practically we have seen that it's not that simple, and that several groups are very rapidly using same terms with a slightly different meaning, what can end up in confusions. And to avoid this, therefore, we have established that group. Furthermore, we have several interest groups, one lower layer group. This lower layer group is dealing with CAN data link layer, physical layer issues. So the reason for this is that we say, okay, we have the international standardization groups, but we have to prepare some input for them. So for example, the CanXL data link layer documents, physical layer documents have been prepared here in our working group. On the other hand, a lot of valuable information is generated during the standardization processes of CanFD, of CanXL, and we try to save this information. And this we do in CAN automation specifications in the corresponding subgroup, so a certain SIG or task force. Yeah. Furthermore, we are maintaining in some groups the higher layer protocol CANopen. They have more or less done their work. They are just doing some maintenance if it's necessary. We have then a spin-off of that group where some people come together that say, well, we are CANopen users, but we want to use CANopen in a CanFD environment. So this is then the IG CANopen FD. And in addition to that, we have also some people using J9039, and they say, well, we have there some input for J9039, and can we, or some connecting points between the CANopen world and J9039. So J9039 related topics, they are then treated in this interest group J9039. You see, we have now several higher layer protocols, CANopen, CANopen FD, J9039. And we think if we're talking about data organization within the devices, then we would say, well, it does not make sense to organize the data in a device depending on the communication interface. And therefore we say, well, why not specifying this in a neutral way, in a bus independent way, and then describing in a second step the mapping of the data on the corresponding communication technique. Furthermore, we have there working group dealing with redundancy, with availability of an application, and more of interest is safety and security, and also this we specify in a certain working group. This is the IG safety and security. So if you are interested in these tasks, then please feel free to contact CAN Automation, to join the groups, and to bring in your expertise. Furthermore, I like to highlight that we have a next International CAN conference next year in spring. It's the 18th edition. It will deal mainly about CAN XL, but it will also take care about other CAN-based topics. So if you're interested, then please come to Baden-Baden on the 14th and 15th of May, and then you can discuss with experts the latest trends, challenges in CAN-based networking. Yeah, so much for the moment. I think this is a good introduction for our topic, the future of CANopen, which will also take place a role in the International CAN Conference. So the program is already available at CAN Automation's website, so if you're interested in that. Yeah, future of CANopen. So what does this mean? And when it comes to the future of CANopen, I like always this application, the application of light electric vehicles, because it summarizes a lot of challenges that we may have today and in future. So first of all, there came in the CAN communication just to allow the charging process so that I can connect a charger and charge my battery. But then very soon we saw, okay, it may be also somehow bidirectional power transfer. I may have also several batteries, not only the power supply, I have the drive. So, and to allow a control and a communication between all of them and then a harmonized process, then we have the CAN inside, or the CAN was used to allow this information interchange among these kind of devices. And as soon as I have a communication system inside, I have a base for added value, for further added value, and I can connect further functionalities, a navigation system, gear, force sensor. I can think about a locking mechanism. I have to think about security and so on. So, and finally, I have a highly dynamical system, because it's at the end of the day, typically the end user who is acting as a kind of system integrator, adding, removing device functionality. And all the devices need now to know a certain self-configuration capability. I need to have a certain degree of security and authentication mechanisms. I need to have a certain update capability. So a lot of functionalities are now required by these kind of rather simple applications. And therefore, it makes sense that CAN is now emerging, that I have a more powerful CAN available, and the current version that is implemented in the CAN controllers is the CAN with a flexible data rate. So what means CAN with flexible data rate, and how does CAN with flexible data rate allow an increased data throughput? So we see this here. The basic principle of a CAN FD is that we have a classical wrapper, let's say. So we're starting in a CAN classic way. So we negotiate who is allowed to speak. So we have there a very simple mechanism in CAN. So I have a CAN identifier. I write this CAN identifier bit by bit on the bus. And if I have a low prior CAN identifier than another one, then this other station will give me an in-bit time response and will say, hey, please stop sending. I have a more prior message than you have. Please stop sending. I'm sending now. And afterwards, you can try to send. So this feature of CAN allows us to do system design in a very simple way. I have just to assign unique numbers, and that's system integration, more or less. But the trade-off of this simplicity is that I have something that is called an in-bit time response. And this in-bit time response is the real limiting factor of the communication speed in CAN-based systems. But when it's clear who is the sender, then I can say, okay, now I enter a certain streaming phase. And this streaming phase I can use to turn up the communication speed to what my physical layer is capable to drive. So in our example here, don't take it too serious, but in this example, we were capable to run up to 15 Mbit. So you see here the conditions. So it's really measured. And then when we have transmitted our data, afterwards, we are switching back to this communication speed, which we used at the beginning in the arbitration phase. So we can give then our acknowledgement in this so-called nominal speed and the speed that was used at the beginning. So this is the basic principle of CANFD. And we see here a comparison between CANFD and classical CAN. And we see there, with regard to the bit fields, it looks completely identical. We have a startup frame field, we have the arbitration field, control, data field, CSC, acknowledge, end of frame. So everything is identical. The only difference is the size of the bit fields. Here we have some bits more, here we have some bytes more, some bits more, but in general, the basic structure is the same. And we see, okay, we have a lengthened data field. We have now the possibility to transfer within one CAN frame up to 64 bytes of data. So, and we see here, somewhere in the control field, we are switching now from the speed that we are using during arbitration phase, so the so-called nominal speed, to the speed used in the data phase. And at the end of the CSC field, we are switching back again in the speed that we have used in the arbitration phase at the beginning. So we have two features to increase the data throughput in CAN-based systems, such as in CANopen systems. So this is the amount of data that we carry in one frame. And to reduce the latency, we have the possibility to switch the data rate. So this was very nicely depicted in a presentation provided by Mr. Florian Hartwig from company Robert Bosch GmbH at the International CAN Conference in 2012, where he showed, okay, look, when you're using a CAN at 500 kilobit, and then you're using a CANFD frame, and you transfer still your 8-byte message, but you just increase the communication speed in the data phase, then you see you can already gain data throughput from 500 kilobit. We turn it up to 4 Mbit in the data phase, and we see here we achieve an average speed of about 1.4 Mbit. So this would mean I can take a classic CANopen FD stick, put it on CANFD and run it with CANFD frames, and I will see I can gain data throughput. If I want to get the full impact of CANFD, then we have to know, okay, we need lengthened frames. So then we see in this example, if we increase the payload of the CANFD frame, then we can achieve in this example up to 2.9 Mbit average speed. So what does this mean? This would not work with an average CANopen stack, but we need an adapted CANopen stack, a CANopen stack that has been adapted with regard to the CANFD usage that is capable to run 64-byte frames. But CANFD does not start just in the higher layer, so that I can say, okay, I open up my CANopen stack to 64-byte, but I have also to think about the physical layer. Higher speeds may lead to physical layer issues. So I have to think about the stub lines, I have to think about impedance gaps, the cable quality. So we have learned that classic CAN has a huge, let's say, failure margin. So I can make a lot of mistakes in system design with regard to the physical layer, but CAN is pretty tolerant and will allow a proper communication. Maybe the physical signals are not that good, they're in a rather bad condition then, but the communication will still work. And this margin for errors, this is reduced enormously by CANFD. So when I use CANFD in particular with a bitrate that exceeds the 1 Mbit, or if I use the bitrate switching, then I have to work in the physical layer pretty precisely. So also in CANFD, this line topology, as it should ever been in CAN-based systems, will work or should work without big issues. Short stubs, line topology. Unfortunately, many of the applications do not operate the CAN in a line topology. So I have started with this example of the bicycle. Typical such bicycles, they have a kind of star point termination in the region where we have the pedals, because this is from the cabling regard very advantageous. So we are more or less such a design. So in many applications, you cannot say, I reduce the cabling or the position of the devices to a line topology. The application determines where the devices reside, and this determines at the end of the day the topology. Therefore, we have also to think about how can we allow also in a CANFD environment such kind of network topologies. So CANautomation has there anyway a specification available. CiA 601 series provides CANFD node and system design recommendations. And there's also one thing mentioned I like to remind you here as well. This is that one. This is the ringing suppression. Well, if you're a little bit familiar with the CAN physical layer, then you will know we have two bit states. We have a dominant state and a recessive one. The dominant state is driven with a differential voltage of 2 volt, and the recessive one is then a differential voltage of 0 volt. But as we see here, we have a driven dominant level, so therefore we have almost no ringing. But then when we have the transition to the recessive bit, we just release, and therefore we have a certain ringing down to the recessive level of 0 volt. So now this ringing may be supported, for example, by impedance gaps, reflections, and something more. And we have now the problem, the faster we want to get, the smaller gets the bit time, and the faster we have to calm down the ringing to allow a proper communication. And therefore, in the context of the CANFD development, the CAN semiconductor manufacturer said, well, we think we can provide some measures to calm down the ringing. And this is called the signal improvement capability, or abbreviated SIG. So there exist CAN SIG transceivers for CANFD, and also in future for CANXL, we will have the SIG transceiver capability. So you should consider them, and then you can also have some crazy network topologies running, like stars, DoubleTree, or whatever. So just keep in your head that this SIG capability calms down the ringing of the recessive bit. Furthermore, you should have in mind that with regard to the ringing suppression transceivers, let's say, so to say, you need some time from the propagation time of your bit for calming down the ringing. And this means you cannot achieve that high bit rates in the arbitration. So if you're using SIG transceivers, then for the arbitration, you're typically limited somewhere at 600 kilobit. And this is something you should remember, but mostly the 1 Mbit in the arbitration phase, in the nominal speed, they are not used. But there exist also some measures to allow this again, but I think for the moment, for this short period of time, this would take too far. Yeah, so this is the SIG capability that is available. There exists something else. There's a question. Well, we have now a lot of experience using CANFD in small networks in the sense engine hood or a little bit larger. But what about using CAN in long-lasting networks which are used in container ships, trains, or something like that? And here we have a working group. This is the working group SIG large CANFD, CANXL topologies. And they have analyzed how fast can I go, how far can I go. So for example, for the cargo ships, they are using CANFD with about 250 meters of cable length. And then it seems at the moment, according to our measurements, that the 2 Mbit in the data phase seems somehow a threshold value because of frequency dependent damping. But currently the group, because of other workload of the group participants, got a little bit stuck. Therefore, reminder from my side, if you are interested in these activities, then join the group, reinitiate the group so that we can have final documents summarizing what can be achieved. But as a moment, or as a good house number, I would say, if you want to go that far, as I've mentioned, then about 2 Mbit, this is somehow a threshold. You see on the slide also some first measurements with regard to CANXL. So there you have a dedicated physical layer, the CAN6XL transceiver. It works a little bit different than the CANFD transceiver, but also here with regard to the thresholds, length thresholds, we see something similar as for CANFD. Just as a reminder, when you think that you want to use CANopen FD based on CANFD, then you should have in mind you have now several CAN generations out there in the field. So I'm using here in the headline the names that are often used in the data sheets of the CAN controllers: CAN 2.0 A, B, passive. So then we have now the CANFD, the non-ISO CANFD and ISO CANFD. And if you have a heterogeneous network, so heterogeneous in a sense that you are in an application where very old devices in, then you may think, well, which kind of CAN is spoken there? So the classical CAN will work always. So classical CAN frames in the base frame format can be communicated by all CAN generations. If you want to use something else, then make sure that this type of CAN is supported. So this is not just valid for the 29-bit identifier, but in particular then for CANFD. So during the development of CANFD, there was, let's say, an early bird implementation available, which can be of these controllers can of course be used as classical CAN controllers, but shouldn't be used as FD controllers. There you should use now the ISO CANFD controller, and you can identify them if they're using the stuff count feed. Just in the data sheet, you have just a short look, and then you see is there a stuff count field included, then you know, okay, they are using the ISO CANFD, CANFD as standardized by ISO. And then only if all the devices are capable to speak the ISO CANFD, then you can use the CANFD in your application. Otherwise, the device is not capable of CANFD. They will interfere, the communication will send error frames, and it will not. So if you are using now CANFD and the data link layer, and you want to use the CANFD to full extent, and then from top of a CANopen protocol stack, then you need an adapted protocol stack. So therefore, we have developed a specification of 1301. And first of all, we thought, okay, we just have to adapt the communication objects, but very soon we saw, okay, it's a little bit more. And when we were developing CANopen FD, we were thinking about, should we do everything that is possible? Or should we just make slight changes, and should we just change there something where we really benefit from CANFD, but we want to keep most of CANopen stable so that we have a high recognition value, that people that are using today CANopen can transfer a lot of their knowledge to CANopen FD. And it was the last one for which we decided that we said, okay, let's keep as much as we can stable and adapt CANopen only on those places where we can really benefit. So we updated, of course, with regard to the section physical layer. So as I've already said, we rely on the results developed for CANFD. Therefore, I said it does not make sense to have there a huge section. Just point to the CANFD system design recommendations and follow them. The only thing that we have to provide that are bit rates. So CANopen FD users don't want to deal with all the bit timing details. Just give them bit rates. In best case, just pair of bit rates, one for the nominal speed, one for the data phase. So just adjust them with a dip switch or a software switch or whatever. And then all the backlying bit timing, this is then already clear because it's standardized in the specification. And in fact, we have it here. These are the new bit timing tables based on the very same time quantum. So this we figured out CANFD works then always pretty stable if you operate in the nominal speed as well as in the data speed on the very same time, based on the very same time quantum. And then you can switch quite easily. And we provided here this table, and you should be capable to run these bit rates together without big issue. And if you don't want to dig into depth of these bit rate switching and these bit timings, then follow just the recommendations. And in many cases, and most cases, CANopen FD should work out of the box. In general, if you want to go into depth, then you find here in the proceedings and the videos from the last International CAN conference further recommendations with regard to the physical layer. With regard to CANopen FD, we can say we kept the CANopen device architecture. So you see here the device architecture as it has already been implicitly available in classical CANopen, but now we have it explicitly written down in the CANopen FD specification. So no big change. We extended it a little bit. So you see here we have now two bit rates, the nominal bit rate and the data bit rate. And furthermore, we have here not only a node ID, but a network ID. But all the rest, more or less, was already there in classic CANopen. So you see here, we have the node ID and a network ID. The network ID we have introduced because devices, CANopen devices, may be part not only of a single network, but of an entire CAN-based network architecture or heterogeneous architectures. So it is more and more important that devices know where they are located in this entire control architecture. And we have in CANopen FD now services that allow the communication over network borders into other networks, and they can address directly devices in a certain network and there with a certain node ID. And base for that is the network identifier that we have added in CANopen FD. The network identifier is assigned in the very same way as the node ID. So it's just a small extension. For example, you can use the layer setting services. So layer setting services have been invented for with the idea to say, okay, there is a host controller maybe, and the host controller monitors its network. And if there's a new device added to this network, then the host controller can get in touch with this device, can get familiar with that device, and can then hand over a node ID and now also a network ID to that device. And as identification, the content of the so-called layer setting services is used. So we see this here. It's the vendor ID, the product code, the revision number, and the serial number, and the device that has this information. This shall now get a corresponding proposed node ID. And for CANopen FD, we updated this mechanism in a way that we said, well, we have now lengthened frames. These are the CANFD frames up to 64 bytes. So we can transfer a lot of more information. And with that regard, we can make a more accelerated recognition service. And we see this example here. We can now say, okay, we know some part maybe already of this so-called LSS address. And we say out in the network, hey, is there a device with that part of the LSS address? And if yes, please give me a next part of your LSS address, the next 4 bits of the LSS address. And therefore, we can go a shortcut in this detection mechanism, which devices are available. So this is the new service LSS switch state selective for FD, that we integrated a response into the CAN identifier, which is used by the addressed LSS server. So the LSS servers, these are the devices which I try to get in touch with, which I try to recognize. And they can use a part of the CAN identifier where they write the next 4 bits of their LSS address. And this way, I can accelerate the detection of devices. And there exists also a mechanism that is based on the extended identifier, so 29-bit. There I can provide already 16-bit of the 128-bit of the LSS address. And this, of course, accelerates the recognition of devices dramatically. Here's just an example how this works then. So I think we can accelerate here a bit here, just you see, okay, I know maybe already the first part, the first 3 nibbles. I'm asking, is there a device out there that equals in the first 3 nibbles with this proposed value? And if yes, then give me the next nibble. And we see here, okay, I provide the next nibble, and the value is then coded in the CAN identifier. We see that here. This is then the next nibble value, and then I can say, okay, I know there's one device out there that has this nibble value as nibble 4, and I can then ask for the next nibble, and so on. And if I do this with the extended identifier and the 16-bit portion, then I can recognize a device within 8 CAN telegrams. And this is a significant acceleration in contrast to existing services for LSS and recognition services. And it's also an example that we can say we not just benefit from the 64-byte so that we get a higher data throughput, but I can also have comprehensive and more sophisticated services that allow then an accelerated handling from a system point of view. Furthermore, with regard to CANopen FD, the network management state machine is identical. We just clarified some things. For example, when do we apply the node ID and the network ID? When do we start up a manager capability? This we just clarified, but this is the same as we had already in classic CANopen. As I've said, we analyzed which services benefit from CANopen, from CANFD, and which not really. So let's say the network-oriented services, they are not really limited by classical CAN, and therefore they can remain as they are. Just the data transport-oriented services, they benefit from CANFD and the additional payload, and therefore we changed them. All the rest was kept stable. We see adaptation of PDOs. So you may know a PDO is determined by the communication parameters and the mapping parameters. So the communication parameters mainly say which CAN identifier is used, and the mapping parameters say what is the reference to the local object dictionary, where in my device do I store the data in certain portions. And this means the mapping table is in a classic CANopen device limited to 64-bit to 8-byte because one PDO is mapped to exactly one CAN message. And we see now here okay, we have now in CANFD the possibility to transfer 64 bytes, so we can extend in CANopen FD the PDO to 64 byte. And this means the only thing I have to do is to open up the threshold value for CANopen FD PDO mapping from 8 byte to 64 byte, and we are done. We can use the entire mechanism, no further change necessary. And this allows us, for example, to put several control words for a drive, multi-drive system, for example, in one single PDO. So I can synchronize the behavior of the drives just by mapping the control word into one single PDO, and all of them receive this control word and are in a very simple way synchronized. Just one use case. With regard to the SDO, it was a little bit more tricky. So nevertheless, we said, well, it's very tricky to update the SDO. And furthermore, we see the SDO has some limitations. So for example, we can have read and write access to all data elements that are available in a CANopen system, element by element, device by device. But it's not possible to have broadcast transfers or multicast transfers. So sometimes this would be very sufficient. For example, if I remember myself on knitting machines where you have up to 100 drives doing exactly the same, it would be very great if I could configure all of them with one access, with one broadcast access, instead of 100 subsequent single accesses that would be very time consuming. We have seen at the beginning a system with a bicycle. This is changed dynamically during system runtime by the end user. So at the moment, of course, we can have dynamic cross communication in classic CANopen, but therefore we would need a so-called SDO manager. Up to now, I haven't seen in any existing system an SDO manager. So in theory, it would be there. Practically only in a small subset they will exist. So therefore, maybe we can have a detour around the SDO manager if we update the SDO. And furthermore, I have already talked about routing. There exists an extension in the CANopen environment. Maybe we could embed this in an updated CANopen FD protocol. And therefore, the outcome was, well, let's throw away the classic SDO and let's think about an updated SDO. And the outcome was the Universal Service Data Object, which has a full function coverage of the classic SDO. But in addition to that, it has the possibility of multicast and broadcast communication. We can have parallel access to the very same or other devices. We can have dynamic cross communication. So if the use case changes, maybe a new device is added, a device can dynamically access this device and can get familiar with that device, the inserted device functionality. We have an inherent routing capability. So all this was added. Why do we have this dynamic cross communication? So in the past, the CAN identifiers of the devices had been determined by the SDO server. Most of the devices were just coming with a first SDO server channel, and the server is determining these two CAN identifiers, and then it's up to me as a user, as a system designer, who shall act as a client to this pair of CAN identifiers for placing the request and getting the answer. In CANopen FD, we said, forget about this system. The CAN identifier is now determined by the sender of the CAN message, and the destination is determined in the data field. There, by the node ID value, I determine who shall receive this telegram, and therefore I can dynamically modify this value without any restrictions, and therefore I can dynamically address any device. So we see this then here, where I see, okay, the first data byte is the destination address, and here I can say, okay, do I want to speak to a dedicated device, or do I address a certain group or all devices in the network? So I think this is a big step forward, very interesting for host controllers, for IoT gateways, that want to access during system runtime dynamically a certain data element somewhere in the system. Furthermore, we try to simplify the SDO here in our universal SDO approach, that we have now a service designed with special regard to byte alignment. We can describe the data with regard to size and data type. So I think we did a good job to that. And we have, as I've said, the expedited, the segmented service, and as well as the block transfer. All of them we have introduced. This one very simplified. Due to lack of time, I cannot go into depth here. And finally, we have also the possibility of inherent routing. We can use a local command processed just in a local network, or that command here that allows us to communicate over network borders in a CANopen network architecture. So this allows directly routing to a certain destination network, and there are certain destination nodes. So this functionality allows us, on the one hand, with the broadcast USDO, to speed up end-of-line production, flashing the devices, as I have the possibility directly during one running SDO transfer to open up a new SDO transfer thanks to a transaction number called session ID. I can also ask what is the progress of my software update. Coming back to our starting use case, where I said how is our devices are added dynamically or removed dynamically from a system, how can I control my system and this dynamic system changes. Therefore, dynamic cross-communication between the devices is very helpful, and this we have thanks to the USDO. Furthermore, we extended the possibilities for diagnostics, so therefore we extended the emergency protocol. You see here in dark green the already existing emergency message from CiA 301 from basic CANopen, and we enriched this information by a timestamp, by a logical device number and the CiA specification number, which specification specifies this error code. And therefore, I have a good mean for very complex devices to put the emergency message into the correct chronology. I can say for complex devices, which part of a device is in trouble. And we have now not only a single entry here for error history, but we have an entire error history domain, which demands, of course, several management objects to say what is the depth of error recording, what is the type of error recording, and so on. Yeah, briefly, you see here all the new objects. I think one object I don't depict it with a specific slide, but it's also of interest in that one here, the 1042, the maximum available payload size. This is a very interesting parameter with special regard to security handling, because here I can have a general mean to say my CANFD frame has not 64 byte, but maybe just 48 byte. And therefore, I save the upper 16-bit just for security tricks, for example, for a variable length of telegrams, for a security trailer or whatever. So can be very interesting. We haven't described yet a specific use case, but this is the intent of this object. Brief to know, CANopen FD devices have to be tested. So therefore, we have a test here at CAN Automation Office. It's just a basic testing of the basic services. And you see first CANopen devices with support, FD support are available. It's just a small set of companies offering something. I know of more CANopen FD projects, but they are typically running a project internally in a way that someone who is using this has all the control interfaces by himself under control, and therefore they are not speaking about it or not allowing us to speak about, because they want to keep it secret that they are using CANopen FD. But I know in several projects where CANopen FD is in use already. CANopen FD provides a lot of new functions that allows dynamic management of CANopen embedded networks. We have enhanced diagnostic capability. And a lot of well-known CANopen functionalities remain unchanged. We are currently releasing a version 1.1. It's should appear, I think, in the next week. And finally, we have also to adapt some extensions. I've mentioned already the layer setting services, document 1305. We are also struggling with the document 1302. How can we use now this new CANopen services, in particular the CANopen FD USDO for more sophisticated accelerated network management? So this we are currently discussing in the IT CANopen FD. Somehow touching these activities, we have some further projects running. This is the generic bootloader and the dual mode redundancy. So we have had the request, can we have a harmonized strategy for doing the firmware update? So for example, if I have a tool or want to offer a tool for firmware updates of CANopen devices, can we do this in a harmonized way for various use cases? So you see here at end-of-line production, in the laboratory, and somehow over the air in a running system at the other end of the world. So various use cases, but nevertheless, basic strategy should be the same. And therefore, we had there a task force bootloader, and they have addressed a lot of interesting items. So for example, how to switch between a normal operation and a bootloader mode. Where can I switch? When can I switch? What about security, password protection, and these things? What about node ID handling in this context when switching between the modes? Which object dictionary entries and CANopen functionalities have to be available in a bootloader mode? What about a rollback function? What about an auto start function? All these items that occur when you implement bootloader and when you think about bootloader in the context of CANopen, they are addressed by this group. The document is currently in a final commenting state, so it's a document 710 if you're interested in these kind of activities. Finally, we have there also, with regards to high availability, the activity of the redundancy group. So they are thinking about dual modular redundancy. So the idea was that we have two or several CAN lines, and we can say, okay, in best case, the high layer protocol has no idea on which CAN line the communication goes. So nevertheless, in any case, the information is distributed via the CAN and the availability of the entire system is increased. So at the moment, we have an idea of this dual modular redundant CAN, and we are thinking about two CAN lines at the moment, the active line and the redundant line, and we will have, as we see here, then the decision in the devices, okay, which one is the active one, which is redundant one, to increase the availability. So this project is almost finalized, but there are some pending issues and we got stuck now. Nevertheless, we are somehow optimistic that by end of the year we will have a proposal for these issues, and then we can restart the group and can update the document beginning of next year. Yeah, future of CANopen has also to consider that one. So CAN is still evolving, and we have presented now in 2021 the CAN XL, the third generation of CAN. So CAN XL is completely backward compatible to CAN-FD. We will also have a so-called protocol exception mode, so that if you have a CAN-FD network and CAN-FD devices see a CAN XL frame, they will just close their ears and will say, okay, there's something strange. I just wait till this passed by, and then when there's the next CAN-FD communication, then I will re-enter. So we are still operating with the 11-bit CAN identifier, but the meaning has a little bit changed. So if you just look at the identifier, it's first of all identical to that what we have in classical CAN. But in CanXL, we just use this for the priority. Therefore, it's called only the priority ID, because the addressing of the data is then done in a dedicated addressing field. And we can address by the addressing field then 2048 byte of payload. So this would allow us tunneling an entire Ethernet frame in CanXL. But addressing is not just done by the address. We have also here, in addition, virtual CAN IDs. This is similar to that what we have seen in CANopen FD, the network ID. And furthermore, we have a so-called service data unit type. This allows us more fine-tuned description of the data content, whether this is related to a specific protocol or Ethernet or whatever. And furthermore, we have several security mechanisms, or in a sense that we have really correct data. So we have a high reliability here integrated in the CanXL. So just to give you a first idea, you see here a comparison of the different CAN generations. At a glance, you see here the first ones, the classical CAN and the CAN FD. As I've already said, they look very similar. Here, a little bit the size changes, but in general, they work almost the same. We have now here the bitrate switching in CAN FD, but that's it. Now in CanXL, it's still somehow similar, at least the wrapper is the same, but we have here dedicated control fields for certain functionality. We have now the CAN identifier for the priority. We have now in the control field the so-called service data unit type describing the protocol. We have the possibility of a certain layer higher function use, like fragmentation, like security mechanisms. We call it CANsec. We have now a specific field for the virtual network allocation, and we have a specific addressing field that allows ID-based addressing, as we did in CAN. We can have a service-based addressing, source destination-based. So various mechanisms are possible depending on the protocols I'm using on top. And then I have up to 2048 byte of data addressable in a byte-wise granularity. In future, of course, it may be the question to use CANopen also in that environment. And you see here furthermore the comparison. How can we accelerate? We see I have now dedicated fields for certain tasks. And I have one thing, we can switch on and off the error signaling in case we want to use the fast mode. So if I want to go on high speed with CanXL, then I do a switching into the fast mode. The CAN transceiver, the CanXL transceiver, drives then actively a dominant and a recessive level, but the wording is then not really correct anymore, because they do not show the nature of dominant and recessive, but I have just, let's say, a 0 and a 1, because both edges are driven. And therefore, we differentiate between the fast mode and the slow mode. And you'll see here, then I can get much higher bit rate. So for example, up to 20 Mbit in the data phase. And here, therefore, I can, if I want to go that fast, I cannot use anymore the error signaling. But these are other details. Therefore, exist other webinars here already on our YouTube channel. For us is then the question, what about CANopen on CanXL? And I think this would be also another webinar if I would go here into depth. First of all, I don't think that we at Canon Automation will start without any initiation from the market. So we won't, or there could be the idea to say, okay, which kind of world of wonders of CANxL do exist and what is theoretically possible. But I think this wouldn't be a good approach. I think we should have some user requests, we should have some requirements from some potential markets, and then we can think about whether and how it is reasonable to update CANopen on CANxL. So if someone is interested on that, I did already a short presentation on this subject at the CiA's anniversary. Therefore, these presentations are available, I think, also on the web. So you can double check and can see what I've said with that regard. In general, of course, I think we would go into a similar direction, that we would say, okay, only update those parts of CANopen which would really benefit. And you see here from another presentation from Bosch that CANxL would provide you a very high data throughput. Of course, it's intended for backbone applications, and here CANxL could act as an integration network, and maybe it could be reasonable at the one or the other application to use CANxL as well. Then I like to remind you on the our social media channels where you could find some information. For example, next week we will be at the SPS in Nuremberg, so you can visit us there and discuss with us your CAN-related questions. You see this here in this slide. We also offer very soon our final open seminar, end of November here in Nuremberg, will be held in German language. So nevertheless, I see most of you, I think, are German speaking people, so you could also attend here. And of course, we have a lot of possibilities offered to you, how to contact us. So if you like, you can contact us and we try to give you more deeper insights on any CAN-related topics. Thank you for the moment. If there are no, I thank you for attending and hope it was interesting, and I wish you all the best for your CAN-related projects. Thank you very much.